Hello, everyone. Welcome to my periodic table trends project, explained by me, Christian Sui. I am a course student who asked for to do the honors pair number 17, elements being period, arsenic, selenium, and my family elements being oxygen and selenium. Let's get started. What is the periodic trends project? This project uses the jigsaw technique, which requires every student within a group to be an active and equal participant for the rest of the group to succeed. To begin, students are organized into home groups composed of four different specialists. Specialists from each home group then reorganized into specialist group that contained only one kind of scientist. Example, group one could include all of the electronegativity scientists, chemists, and group two, all the ionization energy chemists. Each specialist group received a piece of the periodic table in the form of a data table with only a couple facts to guide us. The specialist groups created graphs from data tables, brainstormed explanations for the patterns or trends as you will in the data and reported the results back to their home groups. Together, we took all of this data that we collected individually in our specialist groups to create a concept map in our home groups and explain the design of the periodic table in an accessible and informative way. I was an ionization chemist, as noted by the yellow. This is the periodic table of elements with quickly, this is a period going across with all elements through this being a period and a family of elements defined by the columns, defined by the periods are defined by the rows, families are defined by the columns. These are the labels that we have for each of the elements within the periodic table. So for example, alkaline earth metals, noble gases, actino- actinoids, lanthanides, they're all categorized by different properties per se. So the first part of the concept map is the ionization energy, which is the energy required to release an outer valence electron. Valence electrons are the first to be released because they are the outermost shell and because of the shielding effect. Two periodic trends of ionization energy is that ionization energy of the elements within a period generally increase from left to right due to valence shell stability. The second trend is that ionization energy of elements within a group generally decreases from top to bottom. To connect these ideas, shielding is where like forces repel. So the inner electrons near the nucleus repel the valence electrons on the outside. Shielding connects to levels because the sublevels and orbitals repel the valence electrons on the outermost level. The closer an electron is to the nucleus, the harder it is to extract the electron due to the attraction from the nucleus, and therefore more energy is required to remove it. The first ionization energy of boron is less than that of beryllium, and the first ionization energy of oxygen is less than that of nitrogen. This exception discrepancy is due to the electron configuration of these elements falling under the exceptions rule and because of Hund's rule, filling in the school bus rule. Coulomb's law. Coulomb's law states that opposite charges attract and like charges repel. This is a the distance is inversely proportional to the force and charge is directly proportional to the forms. Coulomb's equation is as follows, which is F equals Q K Q1 Q2 over D squared, where K is Coulomb's constant, 9.0 times 10 to the ninth, n time or nm squared divided by c squared, where Q1 is the point charge -1, Q2 is the point charge -2, r is the distance between two charges. One interesting to note is that this is a physics equation that dictates the behavior of the interactions of different elements. Most notably, within, I believe, the charge of of nuclei and atoms. Atomic radii, essentially the size of the atom. It's the distance between protons and valence electrons. There are two trends here. Across a period, atomic radii decreases due to the increase in a nuclear charge, and down a group, the atomic radii increases due to an increased number of electron shells. To connect these ideas, the size of the radii changes depending on the force of the protons and electrons. To measure atomic radii, we have to measure the distance between the nuclei of two touching atoms and divide that distance by 2. The radii of an atom is determined by the electron configuration of an atom. There's opposite trends here. 1. When going across a period or name, atomic radii decreases, but electronegativity increases. 2. When going down a family, atomic radii increases, but electronegativity decreases. Ionic radii are the size of a charged atom, and the trends are the same as atomic. The the trends of ionic radii follow the same as atomic radii. They're directly connected to ions and isotopes. Electronegativity. The property of an atom that increases with its tendency to attract electrons of a bond. There's two trends here. One, the elements with the highest electronegativity are at the top right, and on the bottom left, the least. Two, most noble gases electronegativity is unknown, as well as electronegativity for lanthanides and actinides. The greater the difference in electronegativity, the more polarized the electron distribution. As the atomic number increases, but force for attraction towards the other electrons as the atomic number increases, force for attraction towards other electrons becomes stronger. Electronegativity and ionization energy share a trend in which both inverse proportionally across a period and decrease going down a family. I was assigned family elements O and SE as part of being as a course student doing pair number 17. Um, yeah. So I identified the element with the higher electronegativity to be oxygen because oxygen has a higher electronegativity than selenium. Electronegativity, as seen by the previous slides, tends to increase as you move to the more to the left to right across a period. Also to note, elements typically that are high in ionization energy also tend to be high in ionization energy. That was a bit redundant. Therefore, since oxygen requires a high ionization energy to release its outermost valence electrons, it is also the most prone to electronegativity, tendency to the tendency to attract electrons. Selenium, Se, or well, I should probably say, family element with the higher atomic radius is selenium. Selenium Se has a higher atomic radius because it is in period 4, which means that it has 4 energy levels, while oxygen is found in period 2, and therefore only has 2 energy levels. Remember, across a period, atomic radii decreases due to the increase in nuclear charge. However, since both elements are in the same family, we must look at the periods, which indicate that selenium is in group period 2. But remember to keep in mind that going down a group, atomic radii increases due to the increased amount of electron shells, therefore making selenium have the higher atomic radius. This can also be seen if we go back to this. So locating selenium and locating oxygen, oxygen is located in period 2, which only contains 2 shells. Selenium is in period 4, meaning that it has four electron shells. The more shells, the bigger the electron radii. And we've established that the bigger the radii, the bigger the atom, which makes oxygen smaller and selenium bigger. Therefore, selenium has the bigger what's it called? Has the bigger radii, atomic radius. Onwards, oxygen. I identified the family element with the higher first ionization energy to be oxygen. Oxygen has the higher first ionization energy. Based on the data that was provided, oxygen has around 600 kilojoules per mole more ionization energy required to release its valence electrons than selenium, only requiring around 950 kilojoules per mole to release its outermost valence electrons. Therefore, oxygen has the higher ionization energy due to the increase in amount of energy needed to release its outermost electrons. I identified the family element with the higher ionic radius to be selenium. As mentioned in the previous slides, ionic radius trends follow the same trends as atomic radii trends. With this in mind, selenium has the higher ionic radius due to ionic trends following the same as, well, atomic radii trends. I identified family element with the higher second ionization energy to be oxygen. Oxygen has the higher second ionization energy. Based on the data that was provided, selenium only reaches around 2,000 kilojoules per mole when releasing its valence requires around 2,000 kilojoules per mole when releasing its valence electrons. Oxygen surpasses this by around an excess of 1,200 kilojoules per mole. Therefore, oxygen has the higher ionization energy, as noted here, with selenium having around 2,000 and oxygen having far beyond that at around maybe an excess 1,500 to 1,200 at around 3,200 kilojoules per mole. For period elements, I was assigned AS and SE because I requested to, as a core student, to try the honors level stuff. So onward. I identified the period element with the higher electronegativity to be selenium. Selenium has the higher electronegativity than arsenic. Electronegativity, as seen by the previous slides, or well, arsenic AS, tends to increase at electronegativity, as seen by the previous slides, tends more to increase as you move more left than right across a period. Or well, I should say electronegativity increases as you move left across a period and decreases as you move right across a period. Also to note, elements typically that are high in ionization energy also tend to be high in, that should really say, electronegative negative energy. Therefore, since selenium requires a high ionization energy to release its outermost valence electrons, it also is the most prone to electronegativity and therefore has the higher electronegativity, which is, remember, the tendency to attract electrons, not the energy required to release them. I identified the period element with the higher atomic radius to be arsenic, As. Arsenic, As, has the higher atomic radius because it is further left in its family. Both oxygen and arsenic are part of the same period, meaning that they have the same atomic levels. However, across a period, atomic radii decreases due to the increase in nuclear charge. Since both elements are in the same family and arsenic is furthest left in its family, and they're in the same period, it has the higher atomic radii. So if we check here on the periodic table of elements, we have arsenic and selenium both in the same period, the same row. However, since they're in the same period, and we noted that atomic radii changes if you move left, increases if you move left, arsenic here is on the left of selenium. Therefore, arsenic has the higher atomic radii value simply because of the trend noted that elements to the left typically have a higher atomic radii than, say, elements to the right, which typically have less, as noted by oxygen in the last example, when in the same, or well, oxygen in the last example when I was mentioning periods. Now, back to where were we? Ah, yes. Therefore, the arsenic has the higher atomic radii, or atomic radius. I identified the period element with the higher first ionization energy to be arsenic. Arsenic has the higher first ionization energy by a mere 3 kilojoule per mole difference, according to the linked graph data. Arsenic has a 944 kilojoule mole requirement to release its valence electrons, while selenium trails with 941 kilojoules per mole to release its valence electrons. Therefore, arsenic has the higher first ionization energy, as indicated by the graph here, with arsenic having a like mentioned here, 3 kilojoule per mole difference. I identified the period element with the higher ionic radius to be arsenic. As mentioned in the previous slides, ionic radius trends follow the same trends as atomic radii trends. With this in mind, arsenic has the higher ionic radius in this case, due to the similarities in trends. I identified the period element with the highest second ionization energy to be selenium, Se. Selenium has the highest second ionization energy by a 261 kilojoule per mole difference. Selenium requires 1,798 kilojoules per mole to release its valence electrons, while arsenic requires 1,537 kilojoules per mole to release its valence electrons. Therefore, selenium has the higher second ionization energy, as provided here by the graph. Thanks for watching. And on a side note, here is the overall overview of both first and second ionization energies. So comparing first and second selenium and arsenic, you can clearly see the difference here, but when noting selenium and oxygen, there's not really much of a actually there is a bit of a difference looking at this graph. But this is an overview that I forgot to include here, and I just wanted to mention that this would have probably been a good idea to include. But other than that, this was my periodic table trends project. Thank you for listening.